Okay, chapter 8. This is linear versus exponential growth, okay? So there are two basic growth patterns. We have linear growth, which occurs when a quantity grows by the same absolute amount in each unit of time. So this is linear. Exponential growth, which occurs when a quantity grows by the same relative amount, that is, by the same percentage unit of time. So let's look at Straight Town. Straight Town grows by the same absolute amount each year, which is 500 people, okay? It grows by 500 people. Now, Power Town grows by the same relative amount, which is 5% each year. So you can see Straight Town, right? It grows by the same absolute amount. So it's linear. It grows in a straight line. And Power Town grows by a relative amount, which is a percentage, and it's exponential. So it curves. Exponential amounts usually curve. Linear, I don't know who all knows this, but linear that's R, means line. That was the worst R ever, so I'm going to try to get rid of it with the big linear means line. A lot of words here, guys. Sorry about that. So the term linear and exponential can also be applied to quantities that decrease with time. In these cases, linear decay means the quantity that decreases by the same absolute amount in each unit of time. And exponential decay, well, it means the quantity that decreases by the same relative or percentage, right? In each quantity unit of time. So for each of the following situations, state whether the growth or decay is linear or exponential and answer the questions about it. So number 1, the number of students at Wilson High School has increased by 50 in each of the past 4 years. If the student population 4 years ago was 750, what is it today? So, I didn't make as much room, did I? Seems like I do that a lot. So A. So it increased, right? It says the number of students at Wilson High School has increased by 50 for the past 4 years. So it increased. By 50. So that implies that it's an absolute amount, right? That implies linear growth. So for 4 years, it grew by 50. So let's do this. 50 times 4. Well, that equals 200. If we add that 200 to the 750, it's 950 students. So that would be our population today. Okay? So that would be the answer for A. So the price of milk has been rising 3% per year. If the price of a gallon of milk was $4 a year ago, what is it now? So it was rising by 3% every year. And it was $4 just a year ago. Right? So let's look at B. So it's increasing by 3%. So since it's a percent, we know that that's a relative amount. And a relative amount suggests what? Exponential growth. So if we have 3%, we're going to have to go 1, 2. Because we have to move our decimal point over, so we're going to take percent equals 0.03. So $4. So we have $4. We multiply that by 0.03. 12 cents. So now we can add that to our $4. $4.12 per gallon. That would be answer for B. All right, C. Tax law allows you to depreciate, which means to go down in value, right? Depreciate the value of your equipment by $200 a year. Purchase equipment 3 years ago for $1,000. What is your depreciated value today? So this is C. So you're going to decrease, right? By $200. So since it's a dollar amount, what does that tell you? That is absolute. That implies what kind of growth? Linear. Not growth. What am I saying? Linear decay. Sorry. Decay. Depreciation, decay. Right on. Okay, I'll get there. So this happened for 3 years. So if we take $200 times 3, right, what's 3? Yes, times 3. That's going to give us $600. So now let's take this $1,000, subtract our 600. That's going to leave our equipment is worth $400. That's what it's worth today. Oh, D. Memory capacity of state-of-the-art computer storage devices has been doubling approximately every 2 years. If the computer's top-of-the-line drive holds 16 terabytes today, what will it hold in 6 years? So doubling. That means that it increases by 100%. That's a percentage, right? Relative amount. Which implies exponential. So it doubles every 2 years. will double 3 times, right, in 6 years, because 6 divided by 2 is 3. So the first time if it doubles, it's going to be 16 plus 16. So that equals 32. Or you could say 16 times 2. Oh, that's 32. I don't know why I just wrote 6, because I was thinking 16 again. Huh. Was it the one to say? No, what I write? This is the first time. Okay. Second time, the 32 is going to double. So that's going to be 32 plus 32. That's going to equal 64. Or you could say 32 times 2, whichever one you want, right? This is going to be the second time. And then the third time, you're going to have 64 plus 64, or you can have 64 times 2, whichever way you want to think about it. Same way. And this is going to be the third time. Okay. So after the third time of doubling, it's going to hold 100 or 120 terabytes. Okay. All right. Now let's look at E. The price of a high-definition TV set has been falling for about, falling by, so it's falling, that means decreasing, by 25% per year. If the price is $1,000 today, what can we expect it to be in 2 years? So it's decreasing. By 25%, so this implies a relative amount. Which implies what kind of decay? Exponential. So we know it's 25%, which equals 0.25. So we're going to take $1,000 times 0.25, which equals $250. Okay, so this is the first year. So we'll take $1,000, subtract the $250, which that will equal $750, right? That's after the first year depreciation. Our TV is worth $750. But we know we're going to depreciate for 2 years, so we have to do that again. So we're going to take this $750, multiply that by 0.25, and that's going to equal $187.50. So this is the second year. So we're going to take the $750 and subtract the $187.50. $562.50 is what our TV will be worth after 2 years. Yeah, I barely made it on space. Sorry, I wrote really little. Sorry if it's hard to see. Okay. Let's look at the impact of doublings. So let's look again at the graph of Powertown's population. So after 14 years, the original population doubled to 20,000. So, Powertown. Wish I lived in Powertown. So After 14 years, so here's 10, this was 15, so 14, we can see that it doubled from 10,000 to 20,000, right? Then it doubled to 40,000, so from 14 to 28, it doubled again to 40,000. And then here, 28, it doubled again. So that is the power of doublings. You see that with exponential, it grows super fast, right? It takes, the time it takes for each doubling depends on the rate of the exponential growth. So that's just the power of the doublings. And it is a hallmark of exponential growth. So you've heard people say, man, that grew exponentially, right? But now you can see kind of what that means, how fast it grows, and how each doubling occurs in the same amount of time, okay? It's pretty cool. All right. We're going to look at some tales, some stories. So the king in ancient times agreed to reward the inventor of chess with 1 grain of wheat on the first of 64 squares of the chessboard. On the second square, the king would place 2 grains of wheat. On the third square, 4 grains of wheat. On the fourth square, 8 grains of wheat. If the amount of wheat is doubled in this way on each of the remaining squares, how many grains of wheat should be placed on the 20th square? Also find the total number of grains of wheat on the board at this time and their total weight in pounds. Assume that each grain weighs 1/7,000 pounds. How many grains of wheat should be placed on the square 20? That's what we're finding. And then how many total grains of wheat should be on the board after the grains of wheat have been placed on square 20? And then we're also going to find the weight, okay? This is kind of cool. We just kind of have to find a pattern, and then from the pattern, everything falls into place. So this is like math puzzles. I don't know. I like it, but so these are the important things. Second square, 2 grains. On this third square, 4 grains of wheat. So we need to figure out some things. So like I said, this is like math games, right? Better if you think of it like that. Or puzzles. Okay, let's start these puzzles. Okay, so let's number our squares. So I'm going to say over here, let's start our squares. And we also have to find grains, right? So let's make a column for grains. And then we also want to know the total. So let's make a column for total. But then, like I said, it's kind of like math puzzles or games. So we're going to have to come up with, we want to see a pattern. So let's make a column. All right, you're going to invent your first formula, okay? Let's do this. I call it fun. You may call it math hell. I don't know. So we're going to have, we know we have square 1. We have square 2. We have square 3. And we have square 4, right? Well, we want to know what's happening on square 20. So let's look at square 1, 2, 3, and 4, and then try to deduce what's happening on square 20. So on square 1, he placed 1 grain, right? Square 1, see, ancient times, with 1 grain of wheat on the first. So he had 1 grain of wheat. But we're dealing with doubling, so we're going to have to deal with everything in the base of 2, right? Because doubling is based on 2s. So if we are going to think about this, we have to say, well, anything raised to the 0 power is always 1. So this is going to be 2 to the 0 power. 2, he placed 2 grains. Right? Well, that's 2 to the first power. Here, if he had 1 grain, that's a total of 1. Well, he had 1 grain here, and he placed 2 more, right? So 2 plus 1, that gives us 3 grains here. Well, on the third square, he gave us 4 grains. 4 is 2 squared. Add 4 plus this 3. So now we have 7 total on the board. Let's look at 4. On the fourth, he gave us, so here we have 8. And that would be 2 to the third power, right? So now to figure out our total, we're going to have 8 plus these 7. So that's going to give us 15. So that's the squares that we know. Now we're going to try to figure out, let's jump to a different one. I like this one. Now we're going to try to figure out what's going on square 20, right? Let's look at this and see if we come up with a pattern. So, the power of our 2, we can notice that every time here, our power is 1 less than our square, right? So, this power of 2 is 0, but our square is 1. This power of 2 is 1, but our square is 2. This power of 2 is 2, but our square is 3. So, every time, our power is 1 less. Our power is 3 here, but our square is 4. So if we continue with this pattern, which we have the whole time, we can assume that when we get to square 20, our power would be what? Our power would be 19, right? So we could look here, see that the power of 2 is 1 less. Number squares. So for 20, I'm going to put it down here, our number of grains is going to be 2 to the 19th. Y'all cool with that? Because for 4, it was 2 to the 3rd. So for 20, it's going to be 2 to the 19th. 2 to the 19th equal, well, let's see. So that is going to be how many grains we have on the board. I don't know if I'll be able to put it there, but I'm going to try. 5, 2, 4, 2, 8, 8. So that's that's the total number of grains we have on the board. It's 5, 2, 4, 2, 8, 8. I didn't have much room. Could have wrote it underneath, I guess. For 2 to the 19th. So when we get to square 20, we're going to have that many grains on the board, right? Because that's one of the answers. So let's write that down. How many grains of wheat should be placed on the board at square 20? Well, 5, 2, 4, 2, 8, 8. All right, we got one answer. Rock on. Okay, now we're going to start looking at this formula. So to figure out the total, so our formula for our total, base with 2's, so this is a 1, right? So if we said, we raise this 2 to the 1, right, minus 1, that would give us 1. Try to find the total grains. So that's what we need to know is total grains. So 2 to the 1 is 2, and if we subtracted 1, that would give us 1. Well, let's try this here. We want 3. So if we said 2 squared minus 1, well, 2 squared is 4, and if we subtract 1, that would give us 3, right? So we're good there. Let's try it again. Go up 1. 2 cubed, we're just going up 1 each time on our powers. So 2 cubed is 8, minus 1 is 7, so that would be right. I'm going to highlight these. These are the numbers we're shooting for. Okay. Let's go up 1 more. So 2 to the 4th minus 1. Well, 2 to the 4th is 16. If you subtract 1, that would give us 15. So that was working, right? Where did I get 1 for my power? For my squares. Right, I'm getting all of these powers from my squares. Here, I take my square and subtracted 1. Here, I use my square power, okay? You're like, did she just pull that number out of her butt? No. I'm trying to base all of my powers for my 2's somehow off my squares. Either use my power for real, take 1 from it. If using the power for real wouldn't have worked, I would have added 1 to it, okay? So I'm using the powers of my squares. Okay. So since this worked and it's working perfectly, I want to now make it a generic formula, right? Just like we did with, like we saw with the n factorial, right? We didn't keep plugging a number in, we just said n was a generic number. So now I'm going to turn this into a generic. And what are we going to do to make our exponent generic? You guessed it, we're going to use n. So to make this be generic, I'm going to say 2 to the n power minus 1. So that no matter what our square number is, we could plug that into here, right? Just like we did here. It was constantly changing. So now we could use any square number here. Cool? So we know now we're wanting to focus on what square? 20. So our total grain formula is 2 to the n minus 1. But we're wanting to focus on square 20. So we're going to say 2 raised to the 20 minus 1. And let's put this in our calculator. 2 raised to the 20 minus 1. Well, that's what we're going to get. And 48,575. Okay. Our total grains. All that came from us developing this generic formula. Okay. Now, let's try to figure out our total weight. So this answer is going to go here. Should be right off the bat. Okay, right on. One more down. Now last one. Phew, long problem, right? I think I'm going to stop after this because, long. Okay, so now, total weight. So we know that the weight, where was it? Is 1 over 7,000. So we're going to multiply that by this number. So we have 1048, 578 multiplied by 1. Okay, let's see what that equals to. Nine. No, it's so wrong. Don't write what I just said. Sorry. Right now, wrong point. 149.8 pounds. Okay. So here. A lot, right? A lot. It's just like puzzles. So like here we know the total number on the board. So we're going to use that to kind of figure out how we can make this formula. So I just used our base of 2 because it's doubling, right? And then I used these numbers as my exponents, subtracted 1 because I knew this got a 2, but my total was 1. So I said minus 1. Then I tried it with the square. That was 4. Minus 1 gave me 3. So that just worked out perfectly. So that's how I went with it, okay? We're going to stop there, and then we're going to pick back up with the leprechaun in a minute.